and the question, I'll directly discuss that. Because some things I write in your answer sheet, but I don't know if you're able to understand everything to it. I try to write the solution there itself in your answer sheets which you share. But if there's still any trouble even after reading that, please just type the name of the assignment and the question number. I'll directly come to that so that our discussion is also done. Otherwise, see, now I shouldn't delay the assignment discussions because at least you both are submitting religiously from this batch. One thing I wanted to discuss was this. Yeah, the graph. This graph often comes. See, this graph is actually related to the whole concept is based on your mathematics. If you are fine, if you're good with your mathematics, then this graph won't trouble you. See, when two things are inversely proportional, first understand a little bit of theory here, then you can relate. When two things are inversely proportional to each other, let's say y is inversely proportional to x. This is inversely proportional. So the kind of graph that we get is hyperbolic graph. Hyperbola means this T shape that is obtained. This is what is a hyperbolic graph. Now problem is that potential is equal to kq by r and electric field is equal to kq by r square. Just a minute, let's just wait. Oh yeah. So electric field is kq by r square. Now see, difference is that the power of the x is different here. Y is inversely proportional to x. So you can have y is inversely proportional to x or y is inversely proportional to x square. Remember one thing. Whenever this occurs anywhere, I just wanted to tell you this so importantly because you can have face any other topic also. So 1 by x cube is there, 1 by x to the power 4. As soon as this power of the denominator increases, the graph's nature still remains hyperbolic because it is inversely proportional. But since the power increases, the graph becomes steeper. You can see the electric field graph is a little steeper from this end. Like this. If you increase the power, it will go like this. If you increase the power like this, it will just keep on going steeper wherever you have. So this often comes, and this is clearly mentioned in your NCRT also, the graph between the potential and electric field and its comparison and differences. So the similarity is that the nature of the graph is hyperbolic for both of them. But the difference is that electric field and electric potential, when you compare it, electric field has a steeper graph. Okay. So write down this properly and just a little bit about the graphs, copy it, that the graph becomes steeper. Potential due to point charge, fifth question, second part. Okay. All right, please copy down this class. I'll discuss the entire assignment. Okay, I'll discuss this potential assignment. I think this you all found a little tough. I'll discuss all the parts. Okay. Okay, just let me know once done. Update me in the chat box, then I'll discuss the assignment. Okay, all right. See, first question. This is a point charge plus Q is at a point O. Okay. See, if the potential difference VA minus VB positive, negative, or zero, you have to see whether the potential at point A is positive or negative. Look, positive charge is there. Formula of potential will be, I'll just write down few hints over here. Rest of it you can copy it afterwards. Let's have a discussion first and then copy it. Okay, first understand this. This assignment is a very basic important assignment that will connect your potential part. So V is equal to KQ by R. This is the formula. And I have discussed with you if potential, if charge is positive, potential will be positive. If charge is negative, potential will be negative. Now charge is positive. So the potential at point A will be positive. And then potential difference, it is at point B. See, due to plus Q charge, the potential at B point will also be positive, because again this is following the same condition. So positive minus positive means this is also positive, this is also positive. So see, that's why the answer here it was positive. Okay, reason is that there is no chance of introduction of any negative charge. So how will you
But
have
like we have R, right? And like VA will be smaller than VB. So like if it's even if it's positive, like the VB is greater than VA and it will become minus. So when you
if
subtract
the
it, will it not be
radius,
minus?
if the radius is greater, we see, then the potential will be lesser. Okay, this is VA minus VB, greater minus lesser. V is equal to
Oh,
QQ by R. Okay, so V is inversely proportional to R. R is more for B, so potential is less. So your
okay, so
VA
VA will be more.
greater, yes. So when you subtract them, eventually it will be positive. It's like 5 is there, this is 2. So 5 minus 2, you will get positive. Okay.
Yes, ma'am.
Okay, second question also, I think it you found it difficult, both of you. See, there's a question from your board exams only. This says n small conducting liquid droplets, each of radius small r, are charged to a potential V each. See, n conducting, we don't know, we have small droplets present, and all of these droplets they coalesce to form one single big drop. Let's say the radius of each small drop, let's say this is r, and one big is capital R. Okay. This says n small conducting liquid droplets, each of radius r, means these, whatever is the number. Okay, number it says take it as n. N is not given. These droplets coalesce to form a single large drop without any charge leakage. Now, without any charge leakage is important. I'll tell you how. It will find the potential of the larger drop. Potential of this bigger drop, let's say V dash, it will also be KQ by R. This will be KQ by R only. Okay, and when we think about the potential of this one, let's say this is K small q by small r. I'll connect both of them and the charges as well. So see, KQ by small r is there, KQ by capital R is there. One has to be converted in terms of another. Now see, if I have a clay, imagine if let's say I have a small amount of clay. Okay, this is a small amount of clay. And if I break it into small parts, very, very small parts, I'm breaking this clay into very small parts. Let's say the volume of this big one was 3 meter cube. If I take these small parts and I add them back, all these small parts that I have broken this into, if I add them back, can you tell me what will be the volume of this bigger one? Not bigger exactly, this one.
3 meter cube.
3 meter cube. Because I have not added any material. I have not deleted any material. So volume remains the same. So here also you have to apply this whole concept only, same similar concept. That is, the volume is going to remain the same. Volume of all these small drops will still be the same. It's like small drops are there. You have added and made a big drop. So volume will be the same. Volume of the small r cube and the capital R1 will be the same. So 4 by 3 pi small r cube is equal to 4 by 3 pi capital R cube. 4 by 3 gets cancelled. Pi gets cancelled. One thing I have not written, n number. 4 by 3 pi small r cube is the volume of one single drop. No, look. 4 by 3 pi r cube, if I talk about one single drop, its volume will be 4 by 3 pi 4 by 3 pi small r cube. But drops are there. So n times these small drops will be equal to this big one drop. So from here we can say we have to write this in terms of the volume, potential of the first one. So potential of the first one is this kq by small r. So we can say this from here, r cube is equal to r n to the power 1 by 3. This relation is clear to all. Hmm? No. Now coming to the potential of the bigger one. Now it says charge has not ceased. I told you this has a significant that without any charge leakage. Means whatever was the
Oh,
charge before.
ma'am, how is it 1/2? Oh, it's 1/3. Okay.
1 by 3 hai. This is 1 by 3 only. Cube root hai na? So 1 by 3. This is 3. Actually the marker here is not very good. This is 1 by 3. Okay.
Mhm.
Charge, it says without any charge leakage, means whatever was the charge earlier will be exactly the same charge. If let's say one single drop has the charge small q, so these many drops will have the charge n into n into small q or n into small q, let's take. So here also the charge will still be n into small q. Okay, this will still be n into small q. And r has a new value here. So I'm writing it over here. Let's put all the values in this. K, n, or let me write it a little bit like this. N, K, Q by R, n to the power 1 by 3. See, this term, K, Q by R is your potential, earlier potential which we took, this one. So if n goes up here, this will be n to the power 1. This will be n to the power minus 1 by 3 into V. So V dash will be, bases are same, powers get added up, 3 minus 2, 3 minus 1, 2, 2 by 3. So n to the power 2 by 3 into potential. Chaos. Clear? Oh, Ishi, have you also
Yeah,
understood?
yeah. Ma'am, one more thing, like the charge of each droplet, why don't we take the total charge as Q and like each particle as Q?
As Q as the total charge, capital Q. Because see, it
Yeah, the
initially mentioned, no, the data is given about the single charge, radius of each charge, radius of each droplet, potential R charged to a potential V each. Even if you take the same thing, let's take the total charge as capital Q. Let's take the total charge. Then you will have to take here NV, same result you will get. I'll just tell you issue. What you're trying to say, I've got it. See, let's take this is the total charge. Here the charge is capital Q. So here also the charge will remain capital Q. Then what you will have to do, the potential that you take, no, V. This V is actually the potential of one single drop. It says they are charged to V each. So how many, if let's say this N is not there because we have
uh, uh,
taken the
yeah, I
charge
got
as
it. I
capital.
got it. Like
Got
the
it?
same value will be there. Yeah,
Yes, same N into V will be there then. Okay.
yeah,
The next question. This I think you all got it, or third question, or any difficulty with the third one? Third one, I think you both got it. Safina wishing. Third one is fine.
yeah, I got.
Safina also did it. Fourth and fifth, we'll see. First, do one thing. Just copy down till here. Then I'll discuss that. Done. See, this says that calculate the potential at point P due to a charge 4 into 10 to the power minus 7 coulomb. Located 9 meters away, hence calculate the work done. It's a very formula based question. Is fourth question fine or any difficulty in this? Is this fine?
I had a problem with the second part. Like,
Second
how do we
part.
know the potential? Like they said, like to obtain the work done, so we need to find the potential for that, right?
Yes.
And like it's saying infinity to point P, so we don't know the radius.
See, infinity to point P. No, 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 no. See. There are two things, potential and potential difference, that we discussed in the last class. One is the term potential, another term is the same thing, potential difference. So instead of directly saying, no, calculate the potential difference or calculate the potential, it can use the term like this, infinity to the, to check whether do you know the definition or not? Do you know the differences or not? See, first part says the charge is there, position is there. Okay, that is your point P. So here I have, look, understand the concept here, calculations you will be able to do. I know. See, this is the point P. Q is there, R is there. Using this data, we will be able to calculate the potential at this point. Correct? Now it says, hence, in the work done in bringing a charge, now charge is given to you. Some amount of charge, Q is given to you. It says, Q is there. This is the amount of charge. This is brought from infinity to this point P. You have to calculate the work done. So basically here when you are writing about the work done is charge into potential or potential difference. Now if something has been brought from infinity to the point, that is just the potential. If 2 points were given, like instead, if it was potential difference, then 2 points would have been mentioned. A point like here P, another point like Q, and the data of Q would have been mentioned, and then you would have calculated VQ minus VP or VP minus VQ depending upon its value. Now, whatever potential you get, you multiply it with the charge. That will give you the work done. So, identifying potential and potential difference, for that purpose, infinity is given. It is not saying calculate it from infinity. For infinity, you have worked and you can never calculate. 1 by infinity is 0. So, you'll never get the answer. And it says, does the answer depend on the path along which the charge is brought? See, answer is no. Reason is that these are conservative forces. Conservative forces, work and potential energy, they are always dependent on conservative forces. What are conservative and non-conservative forces? Recall class 11th. In 11th, you must have done. Conservative forces are those forces which just depend on initial and the final point. That's it. They do not depend on the path travel, whether it's brought from infinity to this or wherever, how it has been brought. It just depends. Okay, first point is infinity, second point is P point. So you don't have to worry about the radius because you just have to see the points, final and initial, because it's conservative. So initial is infinity, final is point P, potential. A point to B point, potential difference. That's it, because these are conservative forces. Conservative potential energy is always calculated in terms of conservative forces. And work done is also changed into the form of potential energy. That's why all these things are based on the conservative forces. Then you have one group is known as the non-conservative force. They aren't conserved, not conserved in the sense certain amount of force or energy is wasted. Like your friction force, it's a non-conservative force. What happens when you rub your palms together? What will happen? The palms will become warm because friction force is generated. That's a dissipative force. So quantities aren't conserved in that. So this is a little bit related to the chapter work, energy, and power. And this basically is trying to identify the differences between the differences between the definition of potential and potential difference. Okay,
So like the V will be the one that we found earlier.
that you've calculated in the first part. Let's take you by because that's the potential. When it is infinity to a point, that is potential. When there are 2 points, then it is potential difference. There were 2 points. It would have given you the data for the second point as well. Then you would have calculated VQ minus V. Right now, only one single. Okay.
So if there was another point given, then we have to calculate it with the
Then you have
radius
to
and all.
calculate here. That value will be given using one you cannot calculate. Then you can calculate VQ minus VP minus VQ depending upon whichever has the greater magnitude. And then the formula of work done would have been Q into delta V, means the change in potential. Okay.
Okay.
It's
Yeah.
just that this data of infinity part has just been given so that you can pick up between these two. And whoever doesn't know this concept of the differences between potential and potential difference will end up using any of it. Sometimes it can be correct, like in this, there is no other option. Sometimes, if other points are also mentioned, it can be messed up. So, just for that purpose, it's okay. Now, clear?
Yes, ma'am. Thank you.
Okay, fifth part may what was the doubt in the fifth part? Could you just repeat, anyone? Safrina, you also had a doubt in this? Fifth, second, you had a doubt. And Oishi, what about you?
I didn't have a doubt on this.
Oh, you were clear with this. Okay. See, Safrina, here you calculate the potential for the E point. This we have discussed. Remember, E point we have already discussed in the class. Similarly, you will get a potential for F point. It says, what is the question? Let me see. Potential at the center, this you know, plus Q minus Q minus Q. You know the answer. You don't even have to calculate by now, right? It is if E and F are the midpoint of both sides. This is E and this is F. What will be the work done in carrying a charge E from O to E and from O to F? See class, O to E or O to F, it says this is basically asking at the center. See, whenever it says no from this point to this point or that point to that point, look here, I'll just write this. Whenever work done is calculated between 2 points, it says no, what will be the work done in carrying a charge from this. See, now it says O to E. This is potential difference. O to F. This is potential difference. So what you do, you calculate the potential you take the charge E, you have to calculate the potential at O, you have to calculate the potential at E. You have to subtract them, greater minus lesser, and then multiply it with this E. Okay, so greater minus lesser, this is how you will have to calculate that. Similarly, this point you're going to take. See, values can be different because this point E is situated here with minus Q plus Q. Here, this is separated with this distance. This is point F here with minus Q here and plus Q with their differences. So you calculate VO minus V, that gives you delta V. You multiply it with it, that gives you the work done. Similarly for point F also. Work done will be the charge multiplied to change in potential. Now, why change in potential? Because 2 points are given. O to F. O is the central point, F is this marginal point. So you calculate the potential at these points. At these individual points you calculate. And then when you subtract it with the center one, that is exactly the work. Then just multiply a charge. E, one more E will be multiplied. E square should be there. Okay, 4 pi has also not been written. Okay, so that must have been cancelled. 2 above and 4 pi below. But just check the options. Don't rely on these options because these some of the questions are actually from your board exams. They are converted in the form of MCQs. They are actually not MCQ based question. Do you think this will come as an MCQ question 1 mark? It's never possible. It's a 5 mark or full-fledged question. 5 marker questions come from this because it's a lengthy question also. You have to calculate O, E, F3 potentials and subtract and then calculate work done. I think E square should be there in one of the options. Okay, E square should be there because one more E you are multiplying. Here, okay, here it is Q. Okay, I get it. One is Q, another is E. Okay, one is Q, another is E. Anyways, concept is clear, so that's why Q into E. If this was also E, these charges, then it would have been E squared. One of them will be Q, other one E, then that's correct. Now got it, Safrina, how to calculate?
Yes.
Okay, so quickly just copy down this part, Toishi, and this part, Safrina. Then I'll discuss equipotential surfaces with you. Okay, now the next topic is equipotential surface. A very easy topic, very, very easy topic. Few properties, learn them as it is they come. But yeah, at one or two places, this can be helpful for the numericals. So, see, anyways, whenever your concepts are right, the questions will, even however they are difficult, some of the part you'll be able to understand. You must have heard of the NEET's paper this year, NEET stuff. Have you heard of this from students or seniors or news and all? So, see, the paper, most of the questions were just from NCRT. It's just that they were lengthy and it was completely conceptual, whatever you study. So, see, equipotential surface, if it has to make it difficult, see, easy question will be what is an equipotential surface? List the properties. The basic, easy, simple question which you all should score. And these questions don't lose marks. Other questions can be in a good numerical where work done is not mentioned, anything about the potential is not mentioned. It will say in an equipotential surface, this theory is there. So you will see, you will think that the question is incomplete because the data is not proper. Reason is that since equipotential surface term has been mentioned, so it should use the properties that you've studied. That I'll tell you while discussing this. Now, the term is itself self-explanatory. That is equipotential. This refers to equi. Equi means equal. This refers to the potential difference, potential and all that you have studied, the whole concept of potential. So equipotential means potential is constant. That is, it is equal throughout. Potential is equal throughout. So there's a surface, let's say, there's a charge q, and at any point I pick, I'm getting the potential as 2 volt. Any point I pick, A 2 volt, B 0.2 volt, C 0.2 volt, D 0.2 volt, like this, all the points, whichever points I'm taking. VA is equal to VB is equal to VC is equal to VD is equal to 2 volt, like this. Or any random surface also. If you have very random surfaces, A, B, C, like this, so they are also equal. VA is equal to VB is equal to VC. Means potential should be the same. The potential's individual values. Now, how is it coming the same? Because of equal distribution of charges, because of equal separation. Don't go into that because you are concerned with the final result. If the final potential is same, it's an equipotential surface. That's it, full stop. Okay. So equipotential surfaces are those surfaces at which every point has the same value of the potential. You pick any point that will give you the same potential. So this way, this helps in the numericals also. If at one point you know the potential and it says this is an equipotential surface, so for the next point you can calculate the potential. I mean, what will you calculate? You will just say same potential, exact value can be taken. Now, few properties are there. First property is that the definition. Potential at every point on the equipotential surface is same. V, A, B, C, all the same. That's the definition. Second one, plus change in potential is not there. So work done will be simply zero. Because there is no change in potential. Final is equal to initial. So change is zero. So work done is also zero. So this is an important point for your numerical. If it says 2 points are there, okay, if it says 2 points are present, and then it says that both of these points, it has given the some history has been given in the question, and it says calculate the work done for the equipotential surface, something like this, where you will feel the question is incomplete. Some more data should have been given by the question so that at least you will reach to a conclusion. No, equipotential, so that is already a hint in itself that potential is the same. Now you derive whatever you can. Third property is that electric field is always perpendicular to the equipotential surfaces. See, why all these points we are discussing, somewhere it can be used, somewhere it cannot be applied. These things we are studying in such a sequence because sometimes the questions have come. Define equipotential surface. See, drawing equipotential surface comes a lot. Most common question is drawing the equipotential surface. Then rarely the properties come from equipotential surface at least, but drawing comes often. I'll discuss this. So wherever the electric field is stronger, the equipotential surfaces are located closer to each other. Wherever there is a gap between the surfaces, then the equipotential surface is weaker there. So weaker electric field, gaps between the equipotential surface, stronger electric field, less gaps between the equipotential surface. This is valid for electric field lines also. Wherever the lines are closer, stronger electric field. Wherever the lines have a gap, weaker electric fields. Okay, drawing equipotential surface. Class, quickly copy down this property till the property part. Then I'll discuss the drawing part of it. Okay, coming to the drawing of equipotential surfaces, this is the most important of all. See, when you have isolated point charges, equipotential surfaces are concentric circles. Okay, so these are concentric circles. So around every charge, these concentric circles are drawn. Plus Q, you have concentric circles. Minus Q, you have concentric circles. There is no difference between positive and negative for an isolated point charge in equipotential circuits. Okay. But when two combination of charges are there, means combination of charges are there, then it will be different. See, if it is positive or negative, means the like charges are together. If like charges are there, two positive charges or two negative charges are there. So see, they tend to repel each other. So because of which what happens, the equipotential surfaces, they are closer towards the periphery. Okay, outer side they are closer. These things you have to draw. That's what the test in this. That because it appears most of the students think these are all concentric circles. That's it. So here these are the outer part. This has closed spaces, while this is the inner part. This has large spaces. Okay, same for the negative charge. Negative positive में difference ऐसे नहीं आएगा. Now, if dipole is there, dipole means unlike charges. And unlike charges, here this is referred to as electric dipole means the magnitude is all this also the same. So you won't be given different magnitudes though. If a different magnitude comes, just increase the number of concentric circles over that side. But that won't come for you. That's not there. In the book is also not there. The difference is that now they tend to attract each other. So from the outer edge, they'll be larger gaps. While from this inner side, there be closed. Closed means close to each other. Then electric field we draw, this is equidistant or uniform. Okay, means this gapping will be the same. All the equipotential surfaces will be lined at equal distances for electric field. And if it is non-uniform, any distance, some is closer, some is not closer. So your here D1 is not equal to D2. And equipotential surfaces have electric field perpendicular, so that's why this is your equipotential surface, this is the electric field. So this gap should be there in your diagram. This 90 degrees should be reflected. These are the things that are checked in these easy questions. That's it. If this comes, that will be the easiest question, one of the easy questions if it comes. So you shouldn't lose marks in here. Okay, that's it. This is all about equipotential. Now, the last part of potential is dipole and energy that I'll discuss. Please draw this. Dipole moment I'll discuss first. The potential of a dipole, just understand the diagram first. Plus q is there, minus q is there. They are separated by a distance of 2a. Here a point P is taken at a general point. We are not taking at axial or equatorial. We can put in the angle. See, the derivation of the electric field of a dipole at a general point is not there in your syllabus. So that's why we didn't discuss it. And we directly did axial and equatorial. In the respective NEET batch, it was completed, the other batch. In this, it was because it wasn't needed. Okay, so that's why whatever is done in this batch in the class, that definitely can come in the exam. It's a part of your syllabus. Whatever are the extra questions for that, we have the JE batch, NEET batches separately. So pay attention in the class, and if there's any trouble with anything, please let me know. Anyways, but potential due to a general point is there in your syllabus. So we'll calculate the potential due to a general point, and then we'll calculate due to axial or equatorial. So this is point P, which is located at some angle theta. Okay, this angle theta to this dipole. We have assumed some separation, let's say R1, which is at A point, and the separation from this B point by distance of R2. Okay, now this construction part, let me explain you. For our calculations, okay, before we move on to this, till here, this part is clear. Plus q is there, plus q is there, minus q is there, a point P is there. This is inclined at some angle theta, which is separated by R. From the center of the dipole to the point of calculation, we take the distance as R. Earlier also we have done. This separation is R1 taken, this separation is R2 taken. Till here, are you all clear?
Yes.
So let me write down the potential first. Potential due to positive charge will be kq by R1. Potential due to the negative charge will be, I'll write it as A and B. VA will be kq by R1, VB will be kq by R2. So net potential will be what class? If I calculate the potential difference here, if I want to calculate their potential difference, or if I want to calculate the net potential at point P. The net potential, I can simply add it VA plus VB. That is KQ by R1 plus KQ by R2. So KQ can be taken common. 1 by R1 plus 1 by R2 is there. So this will be simply will be 1 by R1 plus 1 by R. Okay. Now understand what are these extensions? What are these two lines that have been dropped? Only this is something extra. The rest of it we have discussed. In order to make this derive, the formula derive, see in derivations you are allowed to choose certain values, okay? In derivations you are allowed to make geometrical constructions in order to prove the formula that you get. So here what we do, see if something is like this and like their length is different or same? It will be different. This one will be a little longer than this one. So what is done in order to make it same to it, a little bit it has been extended. That's what has been done over here. Let me explain. Look at this part. PA and PO are not equal because PA is inclined, so it is a little lengthier. Now we have extended a portion OC by dropping AC as a perpendicular. Okay, if AC is the perpendicular, now we can say PA and PC, they are almost equal to each other. That's why we have done this construction, so that we get the two sides same. Is this part clear?
Can you repeat O?
See, PA and PO. I'll mark it. Look here. PA and PO, they are not equal because PA is towards the longer end since it is inclined, so its length is also more. So what we have done, we have extended it to a point at which this both of these are equal. This PC and this PA, they both are equal to each other. So we have dropped a perpendicular AC here. Now clear?
Yes.
Similarly, here this side becomes greater than this side. This is the shorter one now. This is the shorter. This is the longer one. So we take, this is not drawn properly. We take a perpendicular here also so that this PD and PB, they are also equal. Fine till here?
Yes.
Okay. In triangle AOC. Afrina, can you just tell me, if I have this triangle AOC, what will be the value of cos theta?
AC
Huh?
AC by OC.
Theta is this. Base will be the adjacent. OC by hypotenuse is this small a. OC is equal to A cos theta. Clear? Okay. Now see this PC. This PC is made up of PO plus OC. And PC is almost equal to PA according to our geometrical construction. So PC I am replacing with PA. What is the value of PO? Look into the figure and tell me what's the value of PO.
R.
R, yes. This is R. This side, this is R, PO. Plus OC, we've already calculated A cos theta from here. So PA will be equal. Now PA, one more thing. PA also can be replaced. Look, this PA is equal to R1. So R1 is equal to R plus A cos theta. That's the first equation. Okay. Now in triangle small ODB. Oishi, you tell me what is cos theta in the small triangle ODB? Yes, Oishi.
Cos theta.
Yeah, cos theta. This is
Okay, so dB by A. No, dB by OD.
not the cos theta. Base by hypotenuse. Base is the adjacent one to the angle, right?
Yeah, so
OD is the base. This is angle. This is your theta.
oh, okay. I thought it was
Okay.
the upper one.
Oh, this
Okay.
is the perpendicular drop. That is already 90 degrees. Yes. So
Okay.
see OD by OB.
So
Again, this
it's
OD is yes A cos theta, like the previous one. Got it?
yeah.
Now see, this PO bigger one is made up of PD plus this OD, right? This PD plus this OD. So we can say, see, PO is equal to PD plus OD. So PD is equal to PO minus OD. Different? PB and PD are almost equal to each other. PD and PB, they are almost equal to each other because that was our condition for derivation. Now see, PB is what? PB is R2. So this is R2. What is PO? PO is small r. Minus OD is A cos theta. That is the second equation. Now R1 and R2 were something new that we assumed. R is, you can use small r. Small r is what? It's separation from the center of the dipole to the point of calculation. That can be used. But R1 and R2 were nothing. That I just took it, so randomly R1 and R2. So those values have to be replaced. So we can replace, now we have the value of R1, we have the value of R2. Okay. One more thing, class. This is minus Q, no? So potential at P will also be negative. Okay, so they'll be subtracted eventually. Look, one charge is negative. No, we have a dipole over here. So potential will be KQ 1 by R1 minus 1 by R2 because this is the negative charge. So this is your main equation, let's say 3. So now I have the values of R1, R2. If I say put 1 and 2 in 3. So what do I get? If I say V is equal to KQ, let's put it out only, 1 by R1. R plus A cos theta minus 1 by R minus A cos theta. So V is equal to KQ. Let's take the LCM. R minus A cos theta minus R minus A cos theta divided by R plus A cos theta into R minus A cos theta. R will be cancelled. See, minus A cos theta makes it 2A cos theta. K Q 2A cos theta divided by, can anyone identify? There's an identity here. If we can replace here. Any identity you can think of?
A square minus B square.
Yes, A square minus B square is equal to A plus B into A minus B. Okay. So KQ, so this will be R square minus A square cos square theta. Anisa, what is this? Q into 2A. Yes, Anisa? Q into 2A. Anisa, you there? Are you there? Anisa? Yes, no response from you, Anisa. Anyone else? What is this?
Dipole.
Dipole. Yes, correct. This is the dipole. Okay, Anisa, even if you're not sure, that's okay. At least answer in the class. This will help you to remember only. P is equal to Q into 2. I'll tell the correct answer. Or anyone else will help you, but at least respond. Otherwise, I'll think that you have just logged in and you're doing something else. So minus A square cos square theta. This is the whole derivation. Am I clear? Clear? Now, ideal dipole approximation means your size of dipole is very small. Ideal dipole approximation means the size of the dipole is very small. It means plus Q and minus Q, they are located very close to each other. So value of this 2A is so less that the value of A is even lesser. So R becomes very great in front of this A. R square minus A square cos square theta, this has no significance. This is so less. So we write this as R square. So if you put it there in the denominator, Kp cos theta by R square it will be. Now for axial, you can put the angle theta 0 degree for it. So Kp cos 0 degree by R square, cos 0 degree is 1, Kp by R cube. Equatorial surface, 90 degrees the angle, directly 0 because cos 90 is 0. All right. Clear, class?
Yes, ma'am.
Take the screenshot of this because less time is left. Okay, see, let's discuss this question. Yeah. See, this says two charges plus q and minus q are placed at 0, 0, minus a and 0, 0, plus a. Let's locate the charges. Positive charge is present in the negative z-axis at a separation of a from the origin. 0, 0, minus a. This means z-axis. So, negative z-axis. This will be, let's say this is some plus q. 0, 0, negative a. And similarly here this will be minus q, that is 0, 0, plus a, as per the question. We didn't take anything. Then it says potential at a point A, 0, 0, z. So positive 0, 0, z. Now see, very easy, it's just a formula based question. B at this A point will be KQ by C, not Q. If we take P also, that will also help us. See, basically this formula no, that we have studied, this one, Kp by R cube square. This also you can apply directly here. So K, now for P, what you can do? Q into 2A you can write. Kp by R square. So Z square. Second part is potential at y. Now see, for the B part or C part, see all these points are lying on either x-axis or y-axis. So anyways, this will be equatorial. Equatorial. That means potential will be 0. So I'm not marking it. Third is work done in carrying proton from B to C. Potential is 0. Equipotential surface. Work done will also be 0. Fourth point, does work done depend upon the potential between B and C? Between the points, it depends on the initial and final point. The one which I have discussed with you, initial and final points. Okay, not on the point. So a formula-based question, easy question is this. Now, one topic is there, E is equal to minus dB over dr, electric field as a gradient of potential. First, copy down this.
When the second part, they said it's to find the potential of B.
Yeah.
I didn't get that.
Oh, this is just a general point taken, like A at a point on the z-axis, like 0, 0, z. Basically, to tell you that this is lying on the axis of the potential dipole. This is the dipole and it's lying on the same axis. So that's why we're using the formula of the axial point. And other points like B, X, Y, all these are lying on the perpendicular part. So that's why it is equatorial to 0. Okay, just a random question. Means random value. A and Z, these are just random points. Okay?
What? Can you repeat the perpendicular part?
Perpendicular in the sense, see, B point is comma y comma 0. If you locate this point, look, it will be somewhere here. We don't know, the values are not given, x comma y. So see, plane will always be perpendicular to the z axis. This is your xy plane. This is the z axis, right? So it will always be perpendicular to it. So that's why this is equatorial. Similarly, C point is lying on its axis, x comma 0 comma 0. So x axis is also perpendicular to z axis. Why z axis I'm focusing? Because the dipole is lying on the z axis. Okay.
Okay, yeah. Okay, thank you.
Just take the screenshot of this also, class, the question and the solution. Okay, class, we'll continue on Wednesday now. Okay, thank you.
Thank you.